Okay, now here I want to talk about electrical transformers. And what we have to begin with is this idea of a changing magnetic field. So here I have a solenoid, and as you may remember, if I just put a magnet in there, what we'll see is a little bit of voltage is created or a little bit of current, depends on what we're measuring, okay? But if I don't move it, then the voltage just goes back to zero. So there needs to be this changing magnetic field. So what we could get, for example, is if we took a magnet and pushed it in and out, pushed it in and out, in and out, what we're going to get is an alternating current happening within this, okay? Even for one full movement in and out, the current is going to alternate because we've got north passing through this bit and then through here, but then south passes through, so then it flips direction. So we are going to get an alternating current. The mechanics of all that's not super important, but that's the key idea, is we need this changing magnetic field. Now that's very important for the idea of a transformer, and we'll get to that a little bit later. But let's first of all think about alternating current, and we can represent that in a graph. That's one of the points in the syllabus, is if we imagine, okay, we've got time against maybe, well, so this y-axis could be voltage or it could be current. I'm just going to say voltage for this, okay? That means what we're going to get within an alternating current is we're going to get a pattern usually like this. It doesn't always begin at zero. And there we've got a rough sinusoidal 2 cycles. Now, what we might have, for example, let's say up here, this could be 2 volts, and then this could be -2. Now, what that implies is the average voltage is 0. Now, that is true if we're including the direction, but they aren't vector quantities, so that actual average isn't very useful to us, nor is it very true either. So what we get is, so, you know, what we can think about is if we only think about the actual average, we can think about the power, which is current multiplied by voltage. Now, if we take that average voltage, well, that's going to imply that the actual power is 0. Okay, so what we need to do instead is think about the actual averages. Now, you don't need to do that kind of stuff until you get to A level. But what we actually get is if we, well, let's imagine we look at this and we think about just the actual sizes. Well, the actual total size of this comes from this equation. We know that power is equal to current times voltage. We also know that voltage is current multiplied by resistance. So what we can then do is we can combine these two. We can essentially substitute this into here and get P is equal to I times R, or more simply, P equals I squared R. Really, you don't need to worry about all the mechanics of this. This is useful to you if you are given, if you need to calculate power or current or resistance, but you're only given like 2 of these values. You don't, for example, have voltage. And I mean, from this, you could possibly get voltage as well, depending on what you get. But another thing is you may remember that if you square something like this, well, you've got these negative values, so all the negative values become positive. So what we are going to get is something more like this. Ugh, it's horrible, but there you go. So instead of having 2 peaks and 2 troughs, what we now have is 4 peaks. We still have those zeros, so 0 still happens at the same times, but because the whole thing's been squared, we get the actual size of them, so we think that's going to be 4. Okay, so power being current squared times resistance. This is, you know, really, you don't need to remember too much about this. Just remembering these equations will be useful, and recognizing that you will have to use this. This is something you use much, much more with alternating current. This is still useful for alternating current though. So let's come back to this idea of changing magnetic fields. So what we have is, well, this is the basic construction of a transformer. So what we have is the core is made of soft iron. Now, useful, you need to remember the properties of soft iron. Soft iron is easy to magnetize, but loses its magnetism quickly, okay? And that's important. Loses magnetism quickly. That's important because what we need is for this to turn into a magnet. We've got a coil of wire around this, and it is an alternating current. So it's almost as though instead of moving the magnet, we're moving the solenoid around it. But all we're actually just moving is the current, because the current is moving. What that does is it makes it into a magnetic field, which is also changing. And because that's changing, it's like the magnet moving in and out of this. That means it creates a current over here. And the sizes of those currents depend on the number of coils we have on either side. Now, on this side we've got 6 coils. On this side we've got 12 coils. So let's just imagine that then we have got, 10 volts at 4 amps AC. Okay, so what are we going to get on that side? Well, we can relate that quite easily. There's 2 different ways. So what we imagine is that this is 100% efficient, that it loses no energy. And if that's the case, that means the power on this side, so we can say power P should be equal to power S. The primary power is equal to the secondary power. So we can also rewrite that as IPVP is equal to ISVS. So the power on this side is equal to the power on that side. Okay, but we still don't have enough information. Okay, what we can also say is the ratio of voltages should be equal to the ratio of the coils. So for example, if we have VP over VS should be equal to NP over NS. And so using this, what we can do is we can actually find out what the voltage would be on that side. So let's put in the information we've got. On this side we've got 10 volts. We don't know the voltage on the other side is equal to the number of coils on the left, so 6 over 12. This is quite an easy example. There's not much rearrangement needs doing, but I'm going to do every bit of this. But let's just simplify our fraction. So 6/12 is equal to a half, which is okay. So that's 10 over V. Okay, so that just tells us on the opposite side we're going to have 20 volts on that side. And considering that, what we can also see is what the voltage is going to be, because remember, the power on this side, the product of these 2 numbers should be equal to the product of this and the current on the other side. And it kind of makes sense with respect to conservation of energy, okay? So we got more volts, but that means we must have something less, so we must have less current, okay? And what we can see, okay, 10 times 4 is just 20 times 2. And so why is that useful? Well, in this case, let's come back to P equals I squared R, because that's really where it's important when we're thinking about alternating currents. Because what's going to happen is, well, here we've got a step-up transformer. And what that's going to do is that's going to increase the voltage. Why do we want to increase the voltage? Well, we get a smaller current, which means there's less power wastage in the actual power lines. This is generally where we use P equals I squared R. So with a smaller current, we get less wasted power whenever that's being transmitted over big distances. So let's bring that to a sort of example about, about how we'd actually think about this. So we might have, for example, a power station. So that's supposed to be a cooling tower. We've got our reactor, whatever it is, okay? And so what we might get is power being generated at 25 kilovolts. And what will usually happen then is that will get stepped up. So there will be a large step-up transformer station. Okay, so we're going to have quite a large number of coils on this side, but a very large number of coils on that side. And then that's going to leave the transformer at 400 kilovolts. So again, what we've done is, according to P equals I squared R, we've massively decreased the current because we've massively increased the voltage. And what we're going to get is much, much less loss. Much less power loss in the wires. Okay, and then finally that arrives at a substation. It's going to get stepped down to something lower, like maybe 15 kilovolts. So this is a step down transformer. So we've got lots of coils here and few coils there. Step down to maybe 15 kilovolts, and then it gets to a domestic transformer. And again, same as the one before, we've got a large number of coils on this side, a small number of coils on that side, and that is going to be stepped down to about 240 volts. So basically that's it. What you're trying to do is avoid losing power when you transmit energy across long distances. This is the foundation of a big rivalry between, if you've heard of these guys, Nikola Tesla and Thomas Edison, is that Edison really believed in DC. The problem with DC is that you lose a lot of power over long distances. So what you have to have is booster stations all over the place. It's mega inefficient. Electricity generation is fairly inefficient anyway, but using DC over long distances is mega inefficient as well. So hope this helps, but remember, ask me questions if you're stuck on things.